All right, so this is lesson 3 for electric fields. We're going to talk about charged particles in electric fields and how energy changes as they're moving through these fields. So we have a little diagram to kind of help us understand the scenario. So basically, this is Q1, or charge 1, and this is charge 2. So initially, R1 or D1 is going to represent the distance from charge 1 to charge 2 initially. It's going to be at rest. And then over time, charge 2 is going to move to here. So this is still charge 2. It's just moved. And now we have a new distance separating these two charges. Okay, so at R1, the system has electric potential energy because Q2 is initially at rest. So it has no kinetic energy because it's at rest. So in this scenario, the total energy is the electric potential energy initially, okay? And electric potential energy from our formula sheet is this. So K, the constant, multiplied by Q1 times Q2, divided by the distance between them, okay? Now, by the time we get to R2, there is still going to be electric potential energy, but there's also going to be kinetic energy in the form of the moving mass. So because Q2 is moving and Q2 would have some kind of mass, it now has kinetic energy because kinetic energy comes from things in motion. So the total energy is going to be the electric potential energy plus the kinetic energy at this second time, or time 2. So another way we could express this is E total is going to be electric potential energy, which is K times Q1 times Q2 over now our second distance. Sorry, I should have just called this distance 1 and distance 2, plus, well, we know the formula for kinetic energy. It's a half times mass times speed squared. Now this would be whatever your second velocity is, or V2, okay? We know that total energy needs to be conserved. It's not lost. It's always conserved. And we can write out a full expression. So E1 total, or I guess you could have said E total 1, E total 2. They have to be equal though, our initial energy and our final energy. So initially, if we look back, we just had electric potential because the object wasn't in motion. Okay? I'm going to write it out as EE1 plus EK1 because sometimes we will not be at rest. And you don't need the commas, you can just write EE2. Sometimes I write them, sometimes I don't. Sorry for the inconsistency. But if V1 is 0, then EK1 is also 0. So if the object is at rest, this is what our expression would be, okay? As an aside, let's say you were given a voltage difference or a potential difference and you were asked to find the resulting final speed. We would want to get EK2 by itself. And if we wanted EK2 by itself, that would mean we had to subtract EE1, or sorry, EE2 from both sides. So we'd end up with EE1, take away EE2. This is kind of ugly. So if we had EE2 take away EE1, we could represent that as a difference or a delta E. So let's multiply both sides. So we end up with negative EK2 equals potential 2 take away potential 1, which is really change in potential energy. Okay, but we'd want to have EK2 being positive, so if we flip the signs again, we could actually make this equation that might come in a little bit handy. This specifically is not on your formula sheet, and as long as you started with this, you could absolutely do this without having to memorize it, but this kind of manipulation of the formula will come in handy for us, especially if we're trying to find a final speed in these problems. I'll be completely honest with you, when I was doing the daily task, I completely forgot that this is only relevant if your object starts at rest. This actually comes in handy for question 2 of the daily task. Anyways, let's look at an example. We have a small pith ball of a mass of 1 times 10 to the negative 5 kilograms. It has a charge of 8, blah, blah, blah. It's at rest 30 centimeters from a charge of blah, blah, blah. We're going to neglect gravity and air resistance. Awesome. And we need to find the speed that the pith ball will have when it gets to 60 centimeters from the other charge. Okay, let's draw a picture. This will be our Q1, or the charge at rest. We'll have Q2 30 centimeters away, and then it's going to move to 60 centimeters away. So this is still Q2, and this is still Q2. Distance from here to here is 0.300 meters. Distance from here to here is 0.60 meters. So this is kind of like D1, and that's D2. Okay. I'm also going to make a quick list of the info we have. We know that Q1 is the fixed positive charge, so 8 times 10 to the negative 5 coulombs. We know that Q2 is 8 times 10 to the negative 8 coulombs. It also has a mass of 1 times 10 to the negative 5 kilograms. So our energy needs to be maintained through this scenario. So E total 1 equals E total 2. And again, see, I've reversed the letters and the numbers. Don't know why I do this. Well, the total energy at the first stage, well, it's at rest. So initially, the only energy that's going to exist is the electric potential. Let's put kinetic in there and make a quick note that it's 0. Okay. At our second stage, we're still going to have electric potential. We're also going to have some kinetic energy because we're trying to find the speed. So if we're trying to find the speed, that must mean there is some kinetic energy because it's moved. Now, because we're going to be trying to get EK2 by itself, let's rewrite this. So on that first page where I'd kind of got EK2 by itself, this is where that's going to come in handy because we know that kinetic energy has mass and velocity or speed in the equation, and we're going to eventually want to solve for speed. So let's get EK2 by itself. So we take away electric potential 2 from both sides. We're left with EK2 equals EE1, take away EE2. Okay? So for now, let's rewrite this up here, a little more space. We can individually replace both of these with our equation for electric potential, which is K times Q divided by D for both of them. So I'm going to leave this as EK2 for now, so that we don't have too many letters happening. Now the reason we would use this formula instead of just for the point is because we do have two charged objects acting, so we do need to take into account that they both have a charge and that the distance between those charges is changing. So we did this in the previous lesson where we factored out the K just to kind of make our lives a little bit easier. Okay, so let's put in our numbers. So K is 8.99 times 10 to the power of 9. Then we have Q1, which is 8 times 10 to the negative 5 times 8 times 10 to the negative 8, divide by D1, which is 0.3. It's not squared. We'll have the same here, but our distance will change. Okay? Let's solve for EK2. 8 exponent negative 5 times 8 exponent negative 8 divided by 0.3 gives us this. Take away 8 exponent negative 5 times 8 exponent negative 8 divide by 0.6. We get 1.06 all of this. Multiply that by 8.99. Oops. We get 0.09589. And that would be joules. That's EK2. Now we also know that EK2 is equal to half mass V squared. If we want V by itself, it's going to be the square root of EK2 over half M. Divide by half times mass, which is 1 times 10 to the negative 5. I really hope this gives me the same answer as before because I've kind of changed it a little bit. 0.5 times 1 exponent negative 5 is 19178. So square root of 19178. And if we take the square root of that, we get 138 as our V. Okay. If you wanted to break this down and find this, and then find that, and then do the subtraction, that's totally fine. Just for the sake of space, I decided not to. When you're punching in stuff with scientific notation, I do strongly suggest you use kind of like an abundance of brackets, more brackets than you might think are necessary, just to make sure your numbers aren't kind of getting mixed into each other. And where possible, instead of going 5 times 10 exponent, oh my gosh, I'm so out of touch with this calculator, to the power of -6, that's a lot of typing, and that you definitely would have to put brackets around. Your calculator should have an exponent button. So what that does is it types in the times 10 to the power of for you, and then you just hit whatever the exponent is. So for charge, if I wanted to do 8 times 10 to the -8, I would just go 8, exponent button, -8. And it does it for you. So it saves you some time, and it also is more accurate than going 8 times 10 exponent 2. You wouldn't use the exponent button there, you'd use the power button. Okay, sorry, should have said that earlier. Whoop. Uh-oh. Sorry about that. That was very weird. I should have put the light on. Okay, example number 2. What speed will an electron acquire if it falls through a potential difference of 45 volts in a vacuum tube in a hearing aid? Okay. Potential difference. That is going to be delta big V. We're talking about an electron, so we know a couple things about an electron. An electron has a charge of minus 1.602 times 10 to the -19 coulombs. We actually know the mass of an electron too. It's 9.11 times 10 to the -31 kilograms. If you forget these, I think they're on your formula sheet. I didn't bring the formula sheet today, of course, but it's definitely at the top of your daily task. We're looking for speed. Okay, so an electron falling means it's going to be resting at one point before it starts to fall. So let's remember that E1 equals E2, and our E1 would be the potential energy plus kinetic energy. E2 is potential energy plus kinetic energy as well. Now, because it doesn't give us an initial speed, we're going to assume our electron was starting from rest. And here we are again. We have that exact same expression. Okay? So we, this time, have a little bit different information. We have a potential difference. So potential difference is V. If you look on your formula sheet, we do have an expression where change in energy is equal to charge times potential difference. So as long as we know the change in energy, and we're given, we were given the potential difference, we know the charge of an electron, we could solve as long as we knew, what am I trying to say? I don't know what I'm trying to say. We're going to use what we did on the very first page. So this right here. If we are looking for our speed, which is V, which is part of EK, as long as we know delta E, which we can very easily find, we have Q, we have V, we can save ourselves a little bit of time. Okay? In this first example, we had point charges, so we didn't know potential difference. We didn't have enough information to find potential difference. So this is just a slightly different way of using the same information. So we know that change in energy is Q times delta V. So change in energy in this case would be 1.602 times 45. Of course, this is 1.602 times 10 to the -19. Just didn't have enough space. So negative 1.602 exponent -19 times 45 gives us this as a potential difference. would be joules. Okay, so if we could arrange this so that we had it as delta E, let's try that. So if we want to make delta E out of this, we need to get the E's together. So let's take away EE2 from both sides. So we're left with EK2 equals E1 take away E2. Now, of course, for difference, we want to take away 1. So if we just reverse the signs on this, we're going to end up with negative EK2 equals EE2 take away EE1. And of course, this is delta E. Okay? Now, when we're solving for something, it's not nice to have a negative with it. So let's just reverse the signs on here so that we're left with EK2 equals negative delta E. Half mv squared is equal to negative 7.209 times 10 to the power of negative 18 joules. Okay, let's fill in the other information we know. We're looking for v squared. Our negatives would cancel out here. And we would need to divide both sides. Of course, if you wanted to just immediately put in the v equals the square root of EE divided by half m, you could also do that. So I kept this 7.2 in my calculator, but it's negative, so I'm just going to make it positive. Divide by 0.5 times 9.11 exponent negative 31. We get the square root of, we get v squared is equal to 1.582 blah 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 times 10 to the power of 13. Of course, we would need to square root that. Oh no. Square root of 1.582 exponent 13, we get 3,977,436. Or let's put that into scientific notation. We'd get 3.98 times 10 to the power of 6 meters per second. So this is the speed that the electron would acquire if it fell from rest through the potential difference of 45 volts within a vacuum. Okay? When I initially did it, mine was a little bit more scatterbrained, but you could also think of V as V2, or you could just leave it as V. I kind of rearranged it a little bit differently. I don't like that quite as much, so this is why we did it like this. Okay? Okay, conservation of energy for moving charges. When a charge moves from one position to another within a field, the change in electric potential must be accompanied by a change in other forms of energy so that total energy is constant. So if no other forces are acting on a point charge, then as it's moving into an electric field, the sum of kinetic and electric potential is constant. That would be this. Changes in gravitational potential are negligible compared with changes in electric potential when gravity force is much weaker than the electric force. All right, in an electron gun, electrons are accelerated from the cathode to the anode, which is at a higher potential than the cathode. If the potential difference is 12 kilovolts, At what speed do the electrons move as they reach the anode? Assume that the initial kinetic energy of the electrons is negligible. That means EK1 is 0. Okay? So we know that the electric potential difference is 12 kilovolts. Of course, kilo is times 10 to the power of 3. So this actually is 12,000 volts. We're looking for speed again. We're dealing with electrons, so we know their charge. And we know the mass of an electron is 9.11 times 10 to the negative 31 kilograms. So again, total energy has to be conserved. In this case, it told us straight up, initial kinetic energy is negligible. So that means that our total energy initially is just electric potential. And we are back where we started with this equation again. And we're looking for EK2. So we can go through all of the work. So EK2 is equal to EE1 take away EE2, which is really just the change, but with the opposite signs. And from our formula sheet, we know that this is really Q times delta big V. So we're left with EK2 equals negative Q times V. Kinetic energy is half mv squared. If we want to get V by itself, we're going to be dividing by half m. V is going to be the square root of all this. Okay? Same equation as we used in the last one, just cut different corners to get to the same end result. You might be thinking, oh my gosh, there's a negative under the square root sign, but a negative charge beside a negative ends up giving us a positive. All right. So the nice thing when you have it set up like this where all your numbers are already together is it makes it a lot easier to punch in. So 1.602 exponent negative 19 times 12,000 is this, divided by a half times 9.11 exponent negative 31 gives us this under the square root sign, 4.22 blah 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 times 10 to the power of 15, but we need to square root it. So we're left with B equals square root of the answer, which is 6,496, oh goodness, 64,964,737. It's a big number. Let's put it into scientific notation. So 6.50 times 10 to the power of 7 meters per second. I believe this is the last example. We have a proton this time accelerated from rest through a potential difference. Its final speed is 2 times 10 to the power of 6 meters per second. What is the potential difference if the mass of the proton is 1.673 times 10 to the negative 27? Again, this will be on your daily task key if it's not on your formula sheet. Okay, so this time we're looking for the potential difference. Charge of a proton is the same as an electron, just positive. Not the exponent. The exponent is still negative. That doesn't have anything to do with positive or negative number. That just tells us the number is really, really tiny. Mass of a proton is 1.673 times 10 to the negative 27. Usually we just go 1.67. And we know that the final speed is 2 times 10 to the power of 6. So if we remember, kinetic energy ends up being equal to negative Q times V, right? Because we get this. So let's save ourselves from some time and let's just remember this. So EK2, this time we're looking for delta V. So EK2 is really a half mv squared divided by negative Q, a half times 1.673 times 2 times 10 to the power of 6 squared divided by negative 1.602 times 10 to the power of negative 19 coulombs. All right, that expression will give us the potential difference. So 2 exponent 6, square it. So this would be a good example of where you should use brackets. So 2 exponent 6, square that outside the bracket, times 1.673 exponent negative 27 gives us that, times a half. So this is our numerator. Divide by negative 1.602 exponent negative 19. We get a potential difference of negative 20,886. Or 2.09 times 10 to the power of 4 volts, and it is negative. So what you'll find is the potential difference required to move protons is negative, whereas the potential difference required to move electrons is positive. Okay. With the daily task, definitely keep your notes handy, keep your formula sheet handy, and if you have questions, let me know as always.